So now we'll hear from Ben, and he'll tell us more about the. Over to you, Ben.
Thank you very much, Carmen. I'll just share my screen. Okay, hope that's working. Give me a thumbs up, Ruth, if it's looking good. Great. Thank you very much, Ruth and Carmen. So when we were preparing the funding bid for the Hub for Biotechnology in the Built Environment, we knew that it was vital to not only develop new biotechnologies in the lab, but to work across scales and understand the architectural implications and opportunities of these new technologies. And not only to do this theoretically through design, but to prototype at large scale. So it seemed natural that as well as building new labs and new workshops, we should create an experimental house to test our research at full scale. And so the OHM was written into the funding bid. So what we can see on the screen here is the few lines out of the endless pages of funding bid, the few lines where we said we'll build an experimental building. The OHM, about 150 square meters, so a sort of domestic scale building, a living lab, to be built on the Newcastle University campus, but Newcastle and Northumbria universities are very close, so everyone within the HBBE can collaborate and make use of this building. The OHM will be an experimental building which can be reconfigured with building services, building panels and cladding which can be replaced. The OHM will be a focus for HBBE research and a shop window enabling public and industry engagement. So of course, when we got the funding, we suddenly had to make this a reality. So we launched into the fun part, developing the concept for the building, working with colleagues on designing the building. And we quickly realized that many of our technologies are at an early stage of development and aren't ready to be tested in a normal house, in a full sort of domestic environment. And some need more space during development than once they're available commercially in the future, and hopefully they'll be miniaturized and better able to fit into a house. So we developed this concept where we'd have a self-contained living space, small domestic space, a self-contained apartment, the home within our building. Below this, a lab space to process flows of materials from the living space, and surrounding those two spaces, a flexible space for prototyping, building and growing large-scale prototypes. And these three spaces will be protected by the building skin, which of course needs to allow light and air to enter the building and to collect water. Crucially, the skin of the building is designed to be modified so we can fix experimental materials to the inside and outside, with some sections of wall that can be completely removed so we can test complete wall panels, perhaps comprising bio-cemented panels and mycelium insulation. And we got very excited envisaging what this space could look like. So this is sort of a very early artist's impression of how we'd start to inhabit this space. And you can still see the fundamental components, the white volume at the top being the self-contained apartment with pipes coming down into the lab below, and then this prototyping and exhibition space surrounding it. And so we entered into a long process of actually making the building a reality, finding a site on the university campus, gaining planning consent, appointing a design team and contractor, and getting the OHM built. And it wasn't an easy process. I think it's important to be honest and clear about this. The effort involved in creating a new building is enormous, and I was very fortunate to have fantastic colleagues in the HBBE working with me on this. And through this process over the last sort of 18 months, we learned a lot about the construction industry, and we learned a lot about the barriers to doing things differently. And we weren't trying to use novel biomaterials. We weren't trying to do anything really crazy. We were just thinking differently about how a building would be used and modified, and trying to use some sort of less conventional materials. And this made us realize that the construction industry, and by that I mean everyone involved in construction, including architects, engineers, university estates departments, insurance companies, planning departments, are all set up 99.9% of the time to deliver highly standardized buildings. And this might seem obvious to anyone involved in this industry, but until you've really experienced those barriers to innovation, you don't realize how deeply embedded the norms are. And it's vital to understand this if we're actually going to bring new biotechnologies into mainstream construction. So we learnt a lot. And we emerged from this process with a fantastic design team and with a detailed design of a building, quite different to our original concept, but still with the same fundamental ideas, the same spaces within the building, and still meeting our original brief. We then moved into a very rapid construction program this spring, where the building went up very quickly in a few months. And here you can start to see the scale of the building compared to the large university buildings which surround it. It looks quite out of place on a university campus, but we wanted to create a domestic scale space that would in some way feel familiar and homely to visitors. And so last month, the OHM was finished. So just to start talking about a few of the features of the building, we can see concrete panels around the bottom of the perimeter of the building made with low carbon, low cement concrete, which are designed so we can easily fix experimental materials onto the outside of the building. And these panels need to be strong because we have some quite substantial heavy construction materials that we want to test. For example, bioreceptive concrete made from waste materials, which Ruth will talk about later. So we want to be able to fix substantial panels to the outside of this building and test those materials in terms of weathering performance and also the public's interaction with those materials. Some panels of the building are completely removable. You can see the timber panels on the right, which can be completely replaced, the whole thickness of the wall. So we can replace those and test biomaterials as a waterproof skin and insulation. We have large windows, roof lights, and a polycarbonate panel on the south facade, which flood the building with light. And the rainwater pipes, emphasized in red, to show the importance of water to life. And the rainwater from the whole building is collected in a tank for watering growing materials and feeding into other processes. Just a couple of details here. You can see the coming together of the concrete panel with the fixing for experimental panels, the removable timber sections, and the large red rainwater collection system above. Another detail that I particularly like, we need to thank my colleague Armand for this. These are dots on the glass. Certainly in the UK, you have to have dots on glass to stop people walking into large glazed windows. I don't know if it's like that in other countries, or whether people don't walk into windows in other countries, but we have to have these dots. But Armand has designed these individual dots, and each one represents the research of one of the researchers within the HBBE. So absolutely beautiful. We have the sort of fingerprint of each HBBE researcher around the building. Then as we go inside the building into the main prototyping and exhibition space, again, we can see the white volume at the top, which is the self-contained living space, and the lab below. And the white wall of the living space will be used for projections, so we can visualize new technologies or processes within the building for visitors. Within throughout the building services are exposed, the pipes, the wires, the networking cables are all exposed, so they can very easily be reconfigured. For example, adding low voltage cabling powered by microbial fuel cells. The walls are covered with cork and wool boards, partly to reduce environmental impact, to avoid much more harmful cement-based materials, partly to start to introduce visitors to the idea of living with unfamiliar natural materials and surfaces. And also we have exposed fixings, which means that all of the wall linings are removable, so they can be replaced with experimental materials in due course as we start constructing with the materials at this scale. But just a simple detail like this, having an exposed screw and washer holding the wall panels on, is incredibly alien to the way that buildings are normally constructed. Normally every fixing is concealed, making modification difficult and destructive. So just to achieve this kind of detail meant working very closely with the architect and contractor. But in the end, they really bought into this vision and did a fantastic job of achieving what we needed. And the structure of the building is exposed, the primary steel structure in red, but then a lot of timber secondary structure inside. Is exposed so we can easily install and support prototypes within these double height spaces. We can suspend exhibits from the ceiling and so on. As we head up to the first floor, we can go into the domestic space. On the left, we see the kitchen within the self-contained apartment, which will look more homely once it's furnished, once we have a bed and some chairs and we start to really make this into a familiar domestic space. And this area is particularly designed for microbial studies, giving us a realistic domestic space, but with full control over occupancy, natural or mechanical ventilation, material surfaces, and so on. So we have this incredibly controlled environment. There's a washing machine installed there, and the waste pipe from the washing machine feeds into the lab below for an ongoing project on microbial removal of microplastics from wastewater. On the right, in the shower room, we have a toilet, which gets us very, very excited. I never imagined I'd have so many meetings about a toilet. The toilet looks completely normal, but is actually a new prototype product made by Laufen in Switzerland that separates urine and solids within a flushing toilet, which looks and operates exactly like any other toilet, to remove the really fundamental social barriers about collecting human waste and the challenges of getting people to use a toilet if it's any different to usual. So this just looks and feels like a normal toilet, but the urine and the solids go down separate waste pipes, which should really be called resource pipes, not waste pipes, into the lab below. From the apartment, we can move out onto what we call the mesh deck area, flooded with light and heat through the south-facing polycarbonate facade, making it particularly well suited to growing experimental materials, algae, biofilm, and plants. Directly below the apartment is the lab, and if we sort of turn around and look into the back of the lab, we can see pipes coming down from the apartment. And these have now been fitted with sort of valves, so we can tap off the materials coming down the pipes from the toilet, from the washing machine, from the shower, and so on. And in the space, we can optimize processes to convert this waste into energy and valuable materials. Okay, just get this video running. So this video shows a three-dimensional fly-through constructed from a series of 3D scans of the building. And the important thing is that what we have here at the moment is a blank canvas. You know, we have an empty building with a lot of potential, and we've anticipated some of the technologies that will be installed in the building, processing waste, sampling air, replacing materials. But essentially, we've left the building as adaptable and flexible as possible because the research is moving so fast, we're not sure what technologies we'll want to install and test in a few years' time. So the next step is to bring this building to life and start installing prototypes, which Ruth will tell you about shortly. But before I hand over to Ruth, my final comment is that we often talk about this building as OHM 1 and see it not as a sort of an end point, but as a start point in this journey to taking the HBBE technologies and putting them into mainstream construction. So OHM 1 is designed as a space for early large-scale prototyping and experimentation. We're not expecting these prototypes to all succeed. They're not sort of close to market prototypes. They're real experiments we expect to fail and learn. But of course, it doesn't allow us to fully test our technologies. For example, we can't test load-bearing structural materials, we can't test roofing materials, and it's not a real house with people living in it. So we envisage a series of ohms in the future. For example, ohm 2 might be a structure built entirely from biomaterials to demonstrate their load-bearing, waterproofing, and insulating capabilities, and to show the architectural possibilities of these new materials. And it could be perhaps heated entirely by processing human waste. Ohm 3 might be quite different, built in collaboration with housing developers, conforming to standard housing format, and built largely with conventional materials, but testing the integration of certain technologies with mainstream construction. So now I'll hand over to Ruth to talk about bringing this empty building that we see on the left, bringing it alive and trying to make it more like the vision that we had at the beginning of the project. Over to you, Ruth.
Okay. Okay, so can you see my screen? No?
No, I don't think so, actually.
Hold on a minute. It could be because I haven't shared it. Share a moment. Okay. Can you see Ben?
Yeah, I can see myself, so that's good.
Okay. Hold on a minute. Oh. You said this was easy? Share that, and then, okay, slideshow.
There we go.
Is that it?
That's looking nice and smooth.
Great. Thank you so much. Thank you so much, Peter. Okay, I've got YouTube on one side. I've got, I don't know how many screens I've got going on. So anyway, thanks, Ben. That was brilliant. I love to hear you speak about it, especially in a relaxed manner, because that's not usually the tone that we're talking about the ohm in, but it is some achievement even to get it this far. So the Responsible Interactions is a very small team in HBBE, and it is that way because we're working with the other themes in HBBE. We don't need to be big, so we're working with building metabolism, living construction, and microbial environments. And they are the ones who are carrying out the fundamental science and kind of fundamental thinking around this. So our job is to help to scale up and crucially to apply that emerging science and technology to the real world, to build scenarios within the social, societal constructs and contexts that we're within. The ohm plays obviously a very central role in that process, and it's in the ohm, as Ben has said, that we're going to put these prototypes. And again, as Ben has said, it's really about that kind of gradual taking over of the ohm and interchanging the normative traditional building materials and systems and methods of assembly with technologies that will evolve in HBBE. And indeed, and let me say this clearly as well to the world beyond, we are also looking to embed the technologies and research from other groups and other bio enterprises around the world. And if anyone is interested in doing that with us, please get in touch. So I'm going to speak a little bit about the prototypes in a minute, briefly, since I think Carmen will have explained in the timetable. We've also got a slot in the timetable today where you'll be able to visit the posters and they'll give you much more detail about what we're doing on the specific prototypes. And you can see that at the first break after the first speaker. But before then, I want to talk about another type of prototyping that is ongoing around and between the science and the technology, and that is the prototyping of collaboration. So it's clear that in this territory, it requires a great deal of collaboration across a wide range of disciplines. So we've repeatedly heard that the terms inter and transdisciplinary across all of the talks this week. It's been extraordinary to hear that kind of openness to other disciplines and need to work with other disciplines. And some of the speakers have talked about their collaborations as emerging from sometimes serendipitous meetings, sometimes chance encounters, whilst others have talked about working relationships that have been built over time. I think Jenny Sabin spoke on Wednesday. She repeatedly used the term to build trust, so to be in trusting relationships. And in the context of HBBE, however, we don't have that much time, if we're really honest, and we can't really rely on serendipity. And even though we're extremely lucky in HBBE to have quite a diverse and large group of researchers, also, I have to say, a very nice group of researchers, there are still some disciplines and skills missing from us. So the challenge is definitely how can we actively support and to some extent maybe corral that collaboration. Because I think, to be clear, in some instances, we're asking people to leave their comfort zone. Some of our colleagues, in fact, most of our colleagues will have been in one disciplinary grouping throughout their undergraduate, their postgraduate, their PhD, and potentially beyond that. And I can speak from the experience of many architects who only enjoy speaking to other architects. So I know that that is just the way we come through the system. And for some of our colleagues, their workspace is a relatively controlled workflow environment of the lab. And their culture is one of if not multiple authorship. On the other hand, we have some colleagues where their practice is contingent, responsive, unplanned, and defined by a very singular, very creative aesthetic that stems from sole authorship, sole endeavor. So we have a real difficulty, I think, in kind of merging, or not a difficulty, but a challenge in merging these cultures. So collaboration asks all in the prototype teams to set aside at times their jargon and sometimes their need to be the expert in the group. And this is a real big ask, because to enter into discussions where at times you feel on the back foot because you don't quite understand what's going on does require us to be a little bit of humility and a massive amount of trust in the expertise of others. And we have to recognize that jargon, whilst it's extremely effective within our interdisciplinary conversations, it can be a block to collaborative environments. In addition, we're also, the challenge of prototyping collaboration, we're trying to make prototypes not just for, but crucially in the built environment, which of course is a very large, messy, unruly space. It's full of complexity and changing conditions. It's not just a step beyond the design studio and the lab, but to coin a phrase, it's one giant leap into the real world of prototyping, especially within environments like the OHM. So it's an enormous challenge. So here's how we're planning, I think, to prototype these collaborations. I'll take you through this diagram quite quickly. So up till now, we've held a series of sandpit events. We did this all online before Christmas, an incredible feat. Again, Peter, who's in the background today, was at the center of all of that as well. And all of my colleagues trying to make the technology work. And the teams formed at that point. We had 7 in total. Here I'm only illustrating 3, but that's just because I got bored after 3. But to be fair, those teams formed from relatively brief conversations. At that stage, we didn't really know each other too well. Some of the people, I think, ended up in teams more by accident than desire at times. And I think we see these as our proto teams. We've moved through this initial conceptual design, or what I would call brief making phase. We've done our literature reviews, we were well versed in the territory we're about to enter, and we've done some initial material investigations, all of which has been done because we've had very limited access to labs and workshops. It's typically been done in a bucket in the back of the kitchen. And all of the teams have just gone through, we just had an initial phase of feedback from very excellent technical team in the university in terms of how the prototypes might be constructed or how they might be installed in the OHM, and that's helped a lot of teams to formulate what they want to do precisely. We've also trialed very early stage discussions just recently between the prototype teams and a panel of experts from industry, included engineer, an architect and a contractor. Usually such discussions would start much, much later in the process. Actually, if ever, sometimes they don't even ever happen. But we think these conversations with industry, although they may have less direct influence on the prototypes themselves, we're hoping that they will allow our researchers to lift their head from what they're doing and look to the horizon to see where their research might go, to hear the reaction of experts from the construction industry, and really to get a sense of some of the hurdles, questions, also some of the potentials that they might face in future. But the workshop also signals the start of a process of informing industry experts on these emerging technologies. And that's absolutely critical. Obviously, we have a lot more to do than just inviting 3 experts onto a panel, but we're hoping that by running this kind of initial pilot panel, that it will give us some insights. We're just in the phase of evaluating it at the moment and writing that up. It'll give us some insights to the next steps. So this next bit that I'm about to show in the prototyping of collaboration is still an evolving plan, still uncertain of what direction it will fully take, but we wanted to share it quickly with you today for any feedback. So over the coming months, we anticipate that both the teams and the prototypes will evolve and re-evolve. Potentially the expert of some colleagues may play a diminishing role, although I don't think that actually will be the case. I think what will happen is that other people in our team will be drawn more into the process to give us their knowledge and their skills. And they might do that either by doing it through further experimental support, or they might just give us more critical feedback. So I would imagine the teams may actually morph and bring other people in different ways. At the same time, we've started to open up to different audiences, and you can see this black line along the bottom. So for the most part, that's academic audiences or events like this to the biodesign community. But come Christmas or New Year, I think, when the first phase of the prototypes will be complete, and by that stage, I mean complete in a kind of rough and ready, lumpy way, we're aiming to open up ourselves to much more extensive, diverse, inclusive layer of reflective discussion, this time from a much wider range of publics. So more from the industry in terms of industry discussion, and of course, much more of these sorts of events, although perhaps on a smaller scale, more intimate, where we speak to our academic peers and biodesign community. But critically, because we're working with new and relatively unknown technologies, which can generate suspicion and anxiety, what I heard described the other day as fear of the grey goo. We hope we'll be able to start to work with the targeted user groups. For this, we really rely on Carmen's expertise, and we're also going to bring on board a new postdoc in October from a visual communication background who's going to work and support this area of work too. And we're potentially also advertising for new posts in the future. So if you're interested, please watch this space. So from then on, we anticipate that those teams might reform. The prototypes will start to inform one another. They potentially might hybridize. We hope they'll share technologies and learning. And we anticipate that industry, or we hope that other academic partners might come on board. That's kind of these blue and black squares that join the team here in the image. And there might even be people in the audience who want to partner us with this. So again, please get in touch. We're hopeful that one or two of the prototypes might work directly with one or two of the user groups that we start to work with as well. We see this as moving beyond transdisciplinary to become what this work really needs to be, which is transsectorial, trans-societal. And ultimately, our strategy is to learn and share and very deliberately move towards inclusive, responsible culture of co-production. So let me take you through some of the current prototypes. As I say, they can all be viewed in much more detail on the posters on the Miro board at the next break. And the link will come up in the chat on the left-hand side. If you click on that, it'll take you into the Miro. The prototypes are there to test the technology at scale. That's the first and most fundamental purpose of what we're doing. But we want to do that in the complex real world environment outside the lab in the OM. They all act as experiments themselves, whilst also representing potential end applications. But as Ben says, it's unlikely that these first prototypes will come to full fruition, become fully embedded within a kind of commercial setting or, a cultural setting. To that end, the prototypes embody conceptual thinking, early stage science, and applied technology, all to varying degrees. And you'll see that as we go through them. I'm going to show you 6 of the prototypes here from the teams in HBBE, but I also want to say that there are many other prototypes emerging, both from our fellows, from our PhD students, and indeed some of our master's students who are working alongside us in different capacities. And some of which you will have seen in the posters throughout the week. So again, I'd urge you to go back and either engage with the Miro boards or the YouTube videos to see some of the presentations, particularly from the fellows. So this is the first prototype I'll speak about. This is draws very much in Jane Scott's expertise. She's one of our fellows in BioKnit, and she's combining that expertise with the material and computational expertise of others within the team in order to investigate. And you could see how the tunable and structural qualities of knitted fabric can combine and support the growth of 2 microorganisms. In this instance, it's mycelium and bacterial cellulose. All within a textile composite and at an architectural scale. And you can see we're really pushing to go to a larger scale. That's going to be the huge challenge in this. Next is the Biomaterial Ohm. This prototype aims to shed light on the invisible microbial world inhabiting in indoor surfaces, both everyday surfaces and also the new construction materials that will evolve, both with us and with other research teams around the globe. It's going to do this in 2 ways. Firstly, there's one prototype, which is called the Biomaterial Ohm X, isn't that right? It's the BMX, which is going to offer the public the chance to interact with these materials. And the second is the BMP, which is locating samples of the same materials in the ohm for more controlled investigation of the microbial communities over time. So this project really relies on Angie Sherry's expertise alongside her PhD student Beatrix. And it's amazing how Romy and Paula come from textile product backgrounds and are having a huge influence in this work. I think it's probably one of the most integrated teams that we have, and Armand is there to support the development of this and to make sure that this stands up, literally stands up. The next one is biocellular concrete. This prototype develops from previous work that I've been involved in with colleagues at Queen's University Belfast. I co-supervised a PhD there that was done by Elizabeth Gilligan. She's now part of she leads on a spin-out company that's doing extremely well at the moment, based on some of this research. And her PhD developed a bioreceptive concrete that was made from 90% waste. So that's quite some doing from Liz. The concrete then was used in facade panels designed to increase porosity, allowing water and nutrients to permeate and to support the life in the recessed surfaces and crevices of the panel. And in HBBE, we're going to continue this work. I'm working together with Carolina and Ben and others. I mean, Shri and Rory, who are named here, are based in Queens, so we're all working together. And we're going to enhance the design of the panels to create habitats to better suit the plants that we're intending to plant them up with. And we also will begin to investigate and characterize, again with Angie's support, microbiologist who's ecologist, microbiologist, I think. Angie, type in the right title in the chat. So characterizing the microbes that are going to be found in the panels and trying to understand to what extent they contribute to the overall carbonation process that's ongoing on the panel. So concrete in and of itself across its lifetime is continuing this a reaction of carbonation, and the plants that then, and that's enhanced by the design, Liz's design of the concrete, which is very chunky, very anti-smooth concrete in a way, a very different aesthetic, but it's enhanced because we've got an increased surface area, and then we've got plants absorbing CO2 And we've also got microbes, and that's the level that we want to get to in HBBE. This prototype, Healing Masonry, comes very much from Magda's work in microbial induced calcium carbonate precipitation. And again, she's combining her expertise with others in the team who are good at making things visible, interested in trying to make the invisible visible, and also the computational design skills of the amazing Armand. So the prototypes, or in fact it's prototypes in this instance, isn't only investigating the nature and degree of MICCP in masonry materials. They're also exploring the potential to make the up to now invisible healing processes become very visible. And that will then lead to developing a time-based aesthetic language, which for me is quite an astonishing piece of work. And Magda's extraordinary in this instance because not only does she have all the wherewithal from her engineering background and understanding of MICCP, but also she's a real sensitivity and thought and understanding of the cultural context of the conservation of buildings. So it's a really rich mix, this project. This one's bacterial cellulose facade. It's probably our most speculative, definitely the most risky, most likely to fail of all of them. That sounds negative, but we like that. You know, that will give us very rich data. We're also aiming to use, in this one, we're aiming to use bacterial cellulose again as a facade material. That's quite a bit of a challenge because bacterial cellulose is highly hydrophilic. It absorbs about 98% of its weight in water. It's also biodegradable, which is the reason we're interested in it. And of course, for architects, the one thing that we're taught from undergraduate upwards is, one, architecture is about permanence, and two, it's about providing a safe and comfortable haven for its inhabitants. And of course, dampness and moisture is not normally considered to be a safe and comfortable haven for inhabitants. But the consequence of that is that we are taught or trained in a way to drive water and moisture from and off our buildings. And you would have heard that from Jack Gilbert's talk about the desert landscape of the built environment in terms of microbes. So that, you know, that will be the norm. So we're working here alongside Mung's expertise and Josh to better understand the material properties and growth conditions of bacterial cellulose, and also alongside Young Hung and Chris, his PhD student, to start to understand how we might make bacterial cellulose hydrophobic. Again, I point you in the direction of their presentations early in the week. But we also think that we might want to try to embrace this problem and to allow the facade to become a bioreceptive element, at least in some areas. So again, let's see how this evolves. And the final prototype I'm going to show is one called Energizing Waste. And this is led by a team of colleagues from the Building Metabolism Group. We're also combined with the architectural instincts of Pippa, who's one of our RAs, and Maran Sawa, who's a fellow with an architectural background. And I think that makes for a very rich team around this. So this prototype, it's two prototypes. In fact, it could be said to be a collaboration of prototypes, to overuse the word collaboration. It investigates the methodologies for on-demand electricity generation and biogas storage from domestic waste. It will take garden and food waste together with human waste that will come from our separating toilet in the ohm that Ben previously showed, and it will use both an anaerobic biodigester and microbial fuel cells to generate energy for the home. I really urge you to visit the prototype posters at the next break for more detail. So just the last point. Ultimately, we're aiming for the prototypes to collaborate with one another and indeed with the ohm occupants, both human and non-human. This naturally leads us to models of regenerative sustainability and circularity, perhaps not the closed loop that Barbara Imhoff showed, I think, yesterday, really designed for off-Earth endeavours, since we want the ohm to be in collaboration with the neighbouring ohms, to have permeable boundaries, I suppose, where resources can be shared and interchanged. And as this diagram from Nikki, who's an intern with us currently, it's a brilliant diagram. Thank you, Nikki, for providing this at such short notice. We want to move away from this linear system that is so traditional within our built environment that consumes and pollutes, to a much more regenerative, nourishing system that requires less inputs and produces even less outputs. We are in the very early stages of this work, really early stage, and ultimately it relies on us succeeding in our prototyping of collaboration. I mean, this is really where we see collaboration really is so vital. Instead of us thinking as individual agents or even transdisciplinary research teams, this regenerative approach asks that we look for interrelationships right across the spectrum in order to make sense of our endeavors collectively. That, I think, requires much less competition and much more collaboration, and dare I say, responsible interaction.